Basically, I want to talk about my work at the Italian Institute of Technology, and specifically about the Bright Eye project, which is an ERC funded grant. But most important, what I want to do, I want to introduce you a new technology. And specifically, I want to introduce you this a new single photon detector array, which we call a single photon Havre diode array, SPAD array detector, which I hope that at the end of this application talk, because that's a little bit more inside the application, I will be able to convince you that can trigger many new perspectives in fluorescent laser scanning microscopy. So to start, I think that it's not really necessary. I mean, I want to start with the motivation. And I think that it's not really necessary with this audience to try to convince you that anyway, laser scanning microscopy, specifically fluorescent laser microscopy, together with wide field microscopy, is probably the most popular optical microscopy architecture in life science research. So the reason of this popularity, to my opinion, came not only to do the fact that you can combine laser scanning microscopy with fluorescence that we know give you access to molecular specificity and sensitivity during your experiment, but also because you can combine with a lot of different microscopy technique. I'm sure that most of them has been already mentioned during this workshop, but just let me recap really fast. For example, confocal microscopy. So you know that confocal microscopy allow you to work with fixed sample and to navigate inside your sample thanks to the optical sectionability. If you want to go even further deeper, you can combine with two-photon excitation microscopy, which is another leading technique. Then many other techniques, I mean, I'm sure that that's workshop exactly for fluorescent lifetime microscopy. So you know that you can combine with many spectroscopy techniques. So lifetime, spectral ability. So you cannot get access to a lot of other information, not only simple image information. Then you can combine with fluorescent fluctuation spectroscopy if you want to observe very fast dynamics. So, and then again, there will be no time to touch this topic, but you can combine with other super resolution technique like STED microscopy, for example. So anyway, let's say that laser scanning microscopy can be combined with many techniques. At the end of the story, when you sit in front of laser scanning microscopy, you get access to a lot of different information with a very decent amount of combination of a unique combination of special temporal resolution, or special temporal characteristic, which are represented in this radar plot. So you have really spatial resolution, which is the minimum detail that you can distinguish in your sample. You have access to a large spatial range. So how deep I can go in my sample, how big is my sample. I have a good temporal range. I can observe my sample long time. I have a good temporal resolution, which is the fast dynamic that I can observe. And most important, you can get access to many different information from the sample. So imaging is important, but imaging per se doesn't give you data. So what you want data to solve to answer to your biological question. So when I established my group at the Italian Institute of Technology, that was the scenario. So a really nice technique, but to our opinion, this can be further improved. And specifically, this can be further improved when we solve a fundamental limitation of this approach in how it records the data, how you collect image, how you perform your experiment with this microscopy architecture. So that was basically the motivation, but let me go deeper and try to convince you why I'm saying that this microscope can do much better. So this microscope has a fundamental limitation, and I will show you how to solve this limitation. So to do that, let me recap a little bit how it works very fast, a laser scanning microscope. So specifically for a laser scanning microscope. So in a laser scanning microscope, what you have, you take a laser and you focus this laser by an objective lens in your sample, a fluorescent sample. So that means that when you shine this light in a specific point, typically there's a dimension is a diffraction limited region, so it has a dimension of few hundred nanometers. All the molecules, all the fluorophores that are in this region, they start to are excited, and then they start to emit light. This light is collected by the same objective lenses, and then through a series of lenses, a dichroic mirror and other optical element, is projected into the image plane of the microscope. So first of all, that's something that it's when you are dealing with laser scanning microscopy, you don't think about that. But basically, that's a microscope. So there is always an image plane. okay? So that's very important. Here there is an image plane. So that means that this area is imaged in this specific plane. So, but then what you do? So typically then in the image plane, you locate a detector to measure the light. Specifically, let's think that we are using most of the time, that's a photomultiplier tube. And the photomultiplier tube is a detector that integrates all the light in the image plane. So it's clear that this detector is performing an integration across the space. Okay, so yeah, there is something already wrong, so to my opinion, because here you have an image, but then you integrate these images. But the beauty of this detector is that in principle, you have a very fast temporal resolution. You can basically have a signal that at least has some variation in times, because you know that fluorescence is dynamics. So, and this detector allows you to collect dynamics. But then what happened? So typically you have a data acquisition system that what you do, integrate also across time. So even if your fluorescence has some dynamics, you integrate across, for example, the pixel dwell time of your images. So what does it mean that? That's again, so I start with an image that has dynamics, but I end up with a single intensity value. Okay, so that's how then what the continuation of the story in the specific case of imaging. Then you take your beam, use your scanning system to scan your beam across the whole sample that you want to image, and you build up your digital images. So that's the case of imaging, but similar scenario happens also in other technique like fluorescence fluctuation spectroscopy. So basically, what happened? So I try to anticipate you that there is already something wrong on this. Because again, the physics tell you that your microscope is able to provide an image on the image plane of your probed region that can change in time. But what you do, you integrate specifically all the photons that arrive from your probed region, both in time and in space. So an integration, it's something that is always not good in physics. So we came from the revolution of single molecule microscopy. What they do, simply stop to make averaging. And now what we have a system that in principle, from the physical point of view, can provide you the single photon information, so in times and in space, because you have a variation in times here, you have an image here, but then you use some technology that lose this information. So that what they do, they integrate in time and in space. So obviously that's a problem. How we can solve this problem? So what we can do, we can start to using, for example, some single photon detector like APD or SPAD. And in this case, we have a very high temporal resolution, even higher than somehow the photomultiplier for some aspect. So thereby we can sampling our signal photon by photon in time. But what about the space? Again, here I have an image that's a single element detector, it's not a camera, and thereby I'm losing the spatial information. I keep the temporal information, but I'm losing the spatial information. What I can do, I can use a conventional camera. So that's a pixelated detector. Maybe it's exaggerated because that has really a lot of pixels, and I have to make an image of a very small region. But in principle, then I can obtain the spatial information. But what about the temporal information? Nowadays, this scientific camera, are not able to sampling in time photon by photon your signal. So in this case, I can collect the spatial information, but I lose the temporal information. So I have two technologies that are different, can be complementary, but are two different technologies. So at that time, for me, it was clear that we need something different. We need to think a little bit to something new. And then we start a collaboration with the Polytechnic of Milan. We are a group of microscopists, so we know what we need from a detector point of view, but we are not able to develop detectors that are specific for our need. But we clearly have in mind what we need. We need a camera which is able to basically sampling the probe region of a laser scanning microscopy, photon by photon, preserving the exposition, preserving the image, and preserving the photon arrival time. So preserving the temporal information that every single photon can carry out during my experiment. So with this idea in mind, we knocked to the group at the Polytechnic of Milan, and we developed what, in our opinion, was the first single photon camera specifically designed for solving this limitation of laser scanning microscopy. So I will not go too much into the detail of the technology of this detector, this what I'm going to call SPAD array detector, single photon Havre diode array detector. But I want just to fix really well which are the most important property of this detector. So first of all, that's a camera. So it's composed by 5x5 element, very small camera, 7x7 nowadays in our lab, but it's a camera. So it can be used to make imaging of the probe region of the laser scanning microscope. It's a small camera. So what does it mean? That is only 5x5 element, but it's big enough to sample the probe region of your laser scanning microscope, that you know that is only a few hundred nanometers in size. But the other very important property is that this camera is composed by pixels that are completely working in parallel. So we call a synchronous readout because every time that the photon arrives in one of these elements of the detector array, a digital signal is fired to my data acquisition system, independently by the other one. It's like a matrix of SPAD. So it's exactly the same property of your single element, but it's a matrix. So since it's a SPAD, I can get access also to the temporal information, because every time that a photon reaches one of these elements, there is a digital signal that is fired, and this digital signal has a precision of few 100 picoseconds. So for some version, even below 100 picoseconds. So for the first time, I have a detector that is able to sample photon both in space, because I know where the photon arrive in my image plane, and both in time, because I know exactly when the photon arrive with respect to a reference signal with a precision of 100 picoseconds. So this is just to tell you that I don't want to, again, I want to go into detail of the specification, but what I want to tell you that SPAD array is a very mature technique. So it's the same technology that you have in your mobile phone, and if you are lucky, also in your car, because you have a very expensive car. But anyways, the technology that is there, that is going to improve day by day in terms of noise, in terms of sensitivity, and so on. So, but now we have this detector array, and that provide us potentially access to this information, to single photon information, but we need also to record this information. That's another step, important step. So that's the data acquisition of the system has also to change. And specifically what we need to do, we need to implement it, we need to use what is called typically a time tagging data acquisition system. So we have just to think about that for each photon that arrives to my detector array from a specific position of the sample, I need to record this event and associate to this event a temporal stamp with a precision that must be at least the same of or half of the precision of that I talked you about the SPAD, that is in the order of picosecond. So during my imaging, what I will do for each photon, I tag this photon with a temporal stamp. Okay, with a reference signal. Let's call from the beginning of my measurement. But I can do much more, and I need to do much more, because I need also to record other events, not only the photo events, but also all the other events, like, for example, the reference from my, some reference signal for my control unit of the microscope. So, for example, I want to know when my beam moves across the sample. So I want to register such events. And I want also, for example, to know when if I'm using a pulse laser, when I shine this pulse laser, when this pulse arrives to the photon. Sorry, to the sample. So I need to collect all these events and associate with this event a specific time. So, and the time with a precision of the order of picosecond. So when I have this list of events, what I can do, I can transform this list of events in a list of photons. So basically now I can tell you for each photon that arrives that is collected by my detector array, a series of spatial and temporal information. So I will do what we call a photon resolved measurement. So for each photon coming from my sample, I tag it with some spatial and temporal information. And specifically, which kind of information I can tag. So in the terms of spatial information, for example, I can tell you in which position of my sample, from which position of my sample the photon arrived, because I can move my beam across the sample. So I need to tell you where this photon arrived. Then I can tell you where the photon arrived in the image plane, which is something that before was completely lost. Now I tell you where the photon arrived. what we call scanning position and detection position. Then I can tell you also many other temporal information. So for each photon, I can tell you an absolute time from the beginning of the experiment, for example. The photon arrival time with respect to the pulse laser, which is fundamental for fluorescence lifetime. You know, it has been explained yesterday, I guess. But also many other temporal information. For example, the time I arrive with respect to the change of the position of my laser, or the change of intensity of my laser. So anyway, I can invent many different temporal stamps and put in this table. So and now what I can do is not anymore a conventional imaging, because now I don't have anymore an image, but I have a list of photons. But from a list of photons, I can always reconstruct a normal image. So I can always, when I have this minimal granularity of information, I can always reconstruct an information like an image has been done conventional, which unfortunately lose some information. So because I can make an histogram, for example, for each, counting the photon that arrive for each position of the sample. That's a conventional image. Obviously, what I cannot do is if I have a conventional image, to go the other way around. So for the first time now, I have a technology that allows me to get access to this granularity of information that was not possible before. So when we got this technology, that was like a dream in our lab. So, and we start so many projects that are each one specific for some characteristics to try to improve the characteristic of a laser scanning microscope. But we can do only because we have now this information. We have this photon resolved information or single photon information. That's why we call this approach a single photon microscopy. So for the first time, we can collect fluorescent light photon by photon with some spatial and temporal information that was precluded before. So now I think that I have time to tell you a little bit more about these approaches, and specifically to show you some application how to use this information. The first application that I want to tell you is about to try to exploring only the spatial information. For a second, I will discard the temporal information that I told you before. I will just to integrate across the time, but I will not integrate across the space. So, and what I will show you that by using this information, I can implement what is called image scanning microscopy and improve the spatial resolution of a conventional laser scanning microscope without basically introduce any disadvantage. So let me explain better how it works in image scanning microscopy, and specifically how we implement it with our SPAD array detector array. So as I told you before, in a laser scanning microscopy, in the context of imaging, what you do, you scan your beam across the sample. And in this case, for each position of the beam, what you do, you can collect what is called a micro images. So for each position, I count the photon that come from this position, and I do not only count, but I make an imaging of them. So that's what we call micro images. For each point of the sample, we have a micro image. Only a 5x5 image, but 5x5 is big enough to properly sample the proper region, which again, is in the order of few hundred nanometers. So that's a key aspect, because otherwise, if this camera becomes too big, then it's impossible to transfer this amount of information photon by photon. So, but luckily, a laser scanning microscopy, what it's doing is multiplexing information in time. So you don't have to take care more about that. So if I have such a kind of data set, I can also transform this data set in a slightly more intuitive way for people, because most of the people working laser scanning microscopy are addicted to see an image of the sample and not a series of micro images. And specifically what I can simply see any element of my detector array as a pinhole, like in a confocal microscope. And every pinhole is working simultaneously, so in parallel. So there is no any photon loss during the acquisition time, but every single element is basically build up what we call a scanned image. So at the end of the story, after this process, I can see my data set as a collection of 25 confocal images. So since every of these 25 images is a confocal imaging, by definition, it's rejecting a lot of photon, and thereby it has a very low signal-to-noise ratio. But what is important that I have 25 images, I collect in total all this information. So, and thereby what I can do is try to fuse together these 25 images to get high signal-to-noise ratio, and also super resolution and having high resolution. So to fuse this data set, I need to understand, to fuse this image, I need to understand how these images are done. So, and what is the information content of these images? First of all, these images are representing the same sample because we collect basically simultaneously. And then another important aspect that is easy to demonstrate that these images are pretty similar. They different respect each other in terms of the point-spread function. And particularly the point-spread function, especially the one in the center that associate to the center element, are very similar, but simply shifted in space. So what does it mean this? That every image is almost identical, different signal-to-noise ratio, but are shifted one respect to each other. So if I simply take these 25 images and I sum all together, then I'm doing something really stupid because I'm discarding the spatial information that in principle my detector array is able to provide me. But since I told you that these images are very similar, but simply shifted one with respect to each other, what I can do, I can simply shift back, co-register all the images, so that a process that is called pixel reassignment, and then sum them up. So what happens is that, first of all, I get much higher signal-to-noise ratio, because now I take all the images and I merge in a single one. So I take all the photon that my objective lens and my detector array are able to record and put in a single image. So the signal-to-noise ratio raises up. And then at the same time, I improve the resolution because I take all the photon and try to redistribute in a smaller region. So that's the super resolution effect from ISM and also the super brightness effect. So ISM provides me both doubling the resolution respect to a conventional microscope, similar to structural elimination microscopy, and provide me also a nice signal-to-noise ratio. So let's see some example here. So that's a basic example on a cytoskeleton of a Nila cell labeled with ATO647N. So that's a detail. So here you can see the image that I would obtain from a confocal microscope, in which I need to have high resolution to close the pinhole. But if I close the pinhole, I reject a lot of light. Here, this is the same sample, the same let's say, identical condition in which I open the pinhole to collect as much as possible photon, but I'm losing in spatial information and I'm losing in spatial resolution. Here, this graph depicts the intensity profile along this line. As you see, the blue is the confocal, conventional confocal with small pinhole, very noisy, few photon. I open the pinhole, there is an increase of intensity, but anyway, I cannot resolve the fine structure that are in my sample. If I apply pixel reassignment, as you can see, as I told you, there is an enhancement of the signal-to-noise ratio, much higher intensity, and there is also an increase in the resolution. For example, here again, if I plot the intensity along this line, as you can see, this red curve tell me that now I'm able to distinguish two tiny tubular structures that are close by. So we are a group of people working computational science, and thereby we do not only apply basic algorithm like the one that I show you that is called pixel assignment, but we make also more complex but also high-performing reconstruction algorithm, and specifically we apply what is called joint deconvolution. So we try to merge these images also by performing some deconvolution. And again, what we end up is even higher signal-to-noise ratio and even higher resolution. Yeah, just to very fast, as I told you, we can elaborate much complex algorithms. And for example, we are coming out with a series of algorithms that are also able to not only to improve the resolution and the signal-to-noise ratio, but also to remove the autofocus light and thereby to improve the optical section of the microscope and thereby to improve also the axial resolution of the microscope. As you can see here, that's the original conventional image. That's our image after the reconstruction in image scanning microscopy, in which we not only improve the resolution across the lateral direction, but also we remove autofocus background, and thereby we improve the optical section. But the most important property of this technique, as I told you, is becoming somehow for free. So because basically now what I have a technique that is able to provide me information that before was canceled out by the data acquisition system, by the by the detector. So by taking this information, now I can reconstruct an image with higher resolution and higher signal-to-noise ratio without increasing the intensity of my laser, without using a strategy like stent microscopy or without or like single molecule microscopy. So I have an improvement of square root of 2, improvement of 2 in the frequency domain and square of 2 in the space domain, but for free. So I can sit in front of my confocal using my standard sample preparation, doesn't do any change in your sample, and getting higher resolution for the application that you are working on. So that's again tubulin network imaging, that's chromatin organization. As you can appreciate, there is much higher resolution and signal-to-noise ratio. That's another application in neuroscience. As you can see, you can better refine the spine inside your in your sample. Yeah, again, another important aspect, since you improve the signal-to-noise ratio, basically you can reduce the laser that you shine in your sample, and thereby this is also a technique that is much more gentle with respect to lifestyle imaging. So we can make imaging for different time, for different hour with our new system. Something that before we need to use higher dose of light, and thereby at one point we start to photo damage the sample. Okay, yeah, I think that I have still time for showing what other applications. So that's a little bit more into the context of this workshop. In this case, we also take care of the temporal information that we can provide with this SPAD array detector. And specifically, we take care also of the photon arrival time with respect to the pulse laser. So we can get access to the fluorescence lifetime. But before that, I mean, okay, so yeah, sorry. I mean, that's a slide that doesn't make much sense in this context. But anyway, so just to tell you again, this detector array get access to the photon arrival time with a precision of 100 picosecond. So thereby is fully compatible with fluorescence lifetime, which is in the order of nanoseconds. So the temporal resolution of this detector is perfect for measuring the fluorescence lifetime, and thereby getting access to many different properties of your sample, has been already mentioned in the previous talk. So, but basically you can understand environmental parameters of your molecules, such as pH, ion, oxygen concentration, and very important, you can get access also to molecular binding and so on. So you can combine basically structural imaging with functional imaging. So far, so good. But there was a big problem when we started this project. So not only building up the detector, but also building up the data acquisition system, because, I mean, has been already explained about this time-correlated single photon counting card, or this time tagging board, that when we started this project was already on the market, but the problem that there was, they provide only something like a few channel, few elements. So, and now we need 25 channel, in the best case, 49 channel with some new detector. So at that time, doesn't exist an hardware to do that. And I was lucky that during the time, Rosetta Alessandro was in my lab, started a PhD in my lab. I think that you will meet Alessandro in the next day. And he was in charge to develop, let's say, a data acquisition, time-correlated single photon counting, or more specifically, time tagging data acquisition system to manage this huge amount of channel, this 25 channel coming from the SPAD array. When we start this project, we say, okay, what we can do now, FPGA are super cool, and thereby we start using them, which has the big advantage that they can be, let's say, reprogramming them to updated. You can make a very fast prototyping, and another important aspect that they are cheap. So, and I'm happy to tell you that nowadays with 3,000 euro, I don't know how much dollar it is. So now you can have in your lab a time tagging data acquisition system with a 30 picosecond resolution that can be used for in combination with SPAD array, and not only, because that's what we do. We release this project under the open source umbrella. So if you are interested, you can visit our website. And thinking if you want to, obviously, if you want to build up such a system, please contact us. We are really happy to do that. So anyway, we was able to build up our data acquisition system with 25 channel and high spatial resolution, high temporal resolution, so in the order of 30 picoseconds, so well below the temporal resolution of the detector. So I had also this slide because I enjoyed the conversation about time domain and frequency domain. So let's say on the very same FPGA, we build up also a different approach to measure forest lifetime. The first architecture, what we call bright ITTM, is based on similar to what is called a time correlated single photon counting. So you basically measure the start and stop by using some tap and delay line. But in the same FPGA, we also implemented what is called the digital frequency domain, which is an approach that I'm sure that Alessandro Rosetta will talk about. So just to tell you that anyway, I think that the question of time domain and frequency domain is a little bit going to vanish because, I mean, at the end, it's just a different way to collect the data, but the information are there. If you properly implemented them, they get access to the very same kind of information. So I'm happy that Malakrida also show how it's important to have this periodicity, but you can implement in the time domain and the frequency domain in the same way. It's just a question of the implementation and also a little bit about the art. So anyway, now we have this technology in our hand. So we can do super resolution imaging. Again, here you can see the enhancement by image scanning microscopy and confocal microscopy. But more important, we have access also to the lifetime information, because for each photo, we know where it comes in the detector, in the image space, also in the sample space, but we know also when it arrives. So we get access to the fluorescent lifetime. So we can combine functional and structural imaging. So that's obviously is not a nice example. It's just tubulin, so it's not so interesting having access to the lifetime. But let's see other applications. So in our lab, we are working with some application in which we want to use super resolution in combination with lifetime to understand the status of some neuron ion channel. As you know, the lifetime changes the function of the concentration of the ion, and thereby we can use this information to understand where a channel is open or closed. Another application is in the context of understanding the order of a lipid membrane. For example, in this case, we use a polarity-sensitive membrane to understand if the order of the membrane. And you can see here, we have a shorter lifetime in the inner vesicle because it means a disorder, that we have a disorder lipid, while in the plasma membrane, we have a long lifetime because the lipids are ordered. So again, structural information and functional information come together with super resolution. Yeah, I had also this slide because, as I told you, basically, with this system, you can implement any kind of analysis for the lifetime. We implemented the fitting routine, but also we implemented phasor analysis approach, which we found really extremely useful. But I also want this slide to point another important aspect. As I told you, image scanning microscopy provide you super resolution, but very important, provide you also high signal to noise ratio. You have more photon, and thereby your analysis is much robust, as you can see when you compare the phasor for the ISM compared to the phasor of a confocal microscope. So here, for example, also when you make lifetime, the purple indicated that the lifetime failed. And as you can see that the fail in many pixels, why in ISM doesn't fail. The same behavior you can see also when you do phasor analysis approach. So if you try to simply segment it to region, order a disordered lipid, as you can see, you can better segment it when you have a condition of high signal to noise ratio, as you can see also from this detail here. So phasor is a great union with fluorescent lifetime image scanning microscope. Everything can be done in life, obviously. Again, I want to stress the fact that we can irradiate the sample with less light, and thereby we can get access to this. We can perform light cell imaging for a long time. Another application of lifetime in the context of ISM, obviously, is multicolor. That's particularly important because this detector are, apart to be a little bit expensive compared to conventional detector, they need to collect and store a lot of data. So introducing many SPAD array in your system is not the best things that you can do. Thereby performing multicolor imaging by spectrally separate them cannot be the best solution. So we came out with some strategy that nowadays are quite popular. Here, for example, we combine image scanning microscopy with the possibility to do multi-species imaging by separated to fluorophore, depending on the lifetime. So as you can see here, basically I have two fluorophores, star red and star 6035, that can be excited with the very same wavelength and be collected with a single detector. But since they have a different lifetime, then I can separate the photon belonging to one fluorophore from the photon belonging to the other fluorophore with the method that has been before described by Lionel. Then I want to show this another nice example, which is, again, multicolor species. In these cases, there is no difference in lifetime. So I cannot separate by lifetime, the two fluorophore, but I can separate because they can be excited with two different lasers, a blue laser and a red laser specifically. And I can apply this pulse interleaving excitation. What I like to show here, and I want that having also the opinion of people that are working since long time with phasor. So that's an application of phasor in which I'm not exploring the lifetime, but I just simply exploring the fact that I have two pulse interleaving excitation, and I can separately easily use the same theory of phasor approach the two fluorophore. So I have different strategy to use a single detector, but performing multicolor imaging. So with this, I think that I'm almost finished. So because it's 35 minutes. There are other few applications which are in the context of fluorescent fluctuation spectroscopy, which, as far as understood, is a topic that has not been touched during this, will be touched in the next day of this school. So I can just skip this part also because time is spanning really fast. And just to tell you, just to show you another nice application, just which we use this SPAD array detector in the context of to study dynamics, as similar to fluorescent fluctuation spectroscopy, but a single molecule or the single particle level. So fluorescent fluctuation spectroscopy is super nice to study dynamics, but is an ensemble technique. So, and that means that when we extract some parameters, some information about the dynamics of a molecule, of a particle, that's an average measurement. So here what we do, we use our detector array, our SPAD array, and the spatial temporal information provided by them, the photon, the single photon spatial temporal information provided by this detector to implement a single molecule, a single particle tracking. And specifically what we do. So as I told you, basically our detector array can be seen also as a camera, and can be seen as a very fast camera, faster than any other camera. Thanks to this asynchronous readout, basically, I don't have a frame rate. I don't have any kind of frame rate. The only limitation, since it's a SPAD, is that every time that a photon arrives in one element, this element is blind for 10, 20 nanoseconds. That's the only temporal limitation of this camera. So that means that if a particle or a molecule is inside my probed region, I can track it, okay? And I cannot track at any spatial temporal resolution, not any, just limited by the signal to noise ratio as any tracking technique. But there is no limitation from the detector. So, but unfortunately, as I told you, that's a camera that has only 7 by 7 element, 5 by 5. So it's a very small field of view. So I can track the molecule only when in this small field of view, which means few hundred nanometer. Okay, but then the molecule probably will escape to these few hundred nanometer. But the beauty is that this detector array is integrated in a laser scanning microscope. So I have a scanning apparatus. So that means that when the molecule is moving out from so here is moving inside my probed region, then when it's moving out, what I can do, I can use the scanning system, I can use the galvanometer mirror, I can use the stage the objective lens or the stage of where my sample it is to recenter my probed region around the molecule. So I can implement a real-time feedback system that when the molecule moves, I can always recenter into the center of the probed region, like a little bit like a light spot is illuminating an actor on a stage. So I can implement a real-time feedback system that follows my particle or my molecule across basically the whole field of view of my system, also of my laser scanning system, also across the axial direction, because what I can do, I can introduce a cylindrical lens in my system in order to encode the spatial position of the axial spatial position of my molecule or particle inside the images. As you can see here, I have a round shape when it's in the center of my probed region. When it's above, there is an elongation along one direction. When it's below, there is an elongation along the other direction. So I always know where the molecule is in three-dimensional space. But I can do much more. I can tell you also where the molecule is in the lifetime space, because at the same time, I can also track the lifetime of the molecule. So I can understand if the molecule is moving in a different environment and so on. So here is an example not of a molecule, so we are working at a single molecule level now, but here is an example in which I'm tracking a lysosome. That's the field of view of my camera, but since I can move the camera with this real-time feedback system, the effective field of view becomes much larger and in 3 dimensions, okay? And then at the same time, I can measure the fluorescence lifetime, as you can see here. So I can tell you the lysosome is moving, and then maybe if you realize when it's stopping, the lifetime is changing, it becomes shorter, because there is a sort of interaction. The lysosome is doing something. So for the first, not for the first time, but anyway, I have a nice system that is able to track a particle of a molecule or a molecule in 4 dimensions. So with this, I want just to conclude, and I hope that I was able to describe only a few examples of the project running into the lab, which try to leverage this single photon for spatial and temporal information nowadays provided by this SPAD array detector. So here is the list of publications, if you are interested, which are also in the concept of stimulated emission depletion microscopy, in the concept of single molecule imaging and tracking, for adaptive optics, for 2-photon excitation microscopy. So basically, we saw that this information can be beneficial for any technique combined with laser scanning microscopy. So, and that's the very last one of the last slide. So I'm happy to share with you this slide because as a lab, we really believe that that's a technology that can change the way how to do laser scanning microscopy, but only when it's in the hands of many people like Malakrida, people like Raton, people like many of the people that are listed in this magnificent workshop. So thereby we run a series of open science projects to build up the microscope. So that's a CAD system, which we are able also to provide you the list of components from Torlab. So you basically can build up your laser scanning microscope. We can provide both the data acquisition system and also the microscope control software. And also we are starting also to use Napari to analyze our data. And at the moment, we do not work so much in the context of lifetime because we know that there are groups that are doing these things and also doing much better than us. And so we are also happy to collaborate. But anyway, the key message is that we try to really share as much as possible this technology in terms of hardware and also in terms of software. And finally, I mean, this is really the most important slide. Nothing that I show you can be done without the job of this fantastic team, which include also people from the startup of the IT, the General Instrument. And obviously, I have to admit that also a lot of this result came out also because I got good funding from company, and not only, but also from many European and national agencies. And just finally, I want to thank you for your attention.